Okay, so let us now start our new topic. And previously we have found the efficiency of a half wave rectifier. Now in today's lecture we'll try to find the expressions for finding the efficiency of full wave rectifier. So earlier in our discussion in lecture 1 we have discussed about the working principle of different kind of rectifiers. Then in lecture 2a there we have found the full wave half wave rectifier efficiency, and 2b, that is in this lecture we will be finding the full wave rectifier efficiency, and after that we will be finding the ripple factor in next lecture. Now to reduce the video timing I have pre-filled this, and rectification efficiency of a rectifier, it is defined as the ratio of the output DC power to input AC power. So expression for this output DC power which is appearing across the load resistance, hence output DC power can be defined as I square DC into RL, and input AC power, it is the current flowing through the entire all the resistance in this circuit. So that is your load resistance as well as diode forward resistance and the source resistance. So I square RMS into all the sum of all the resistance, so that will give us the input AC power. Now if we have a look into this particular waveform circuit diagram, I have not drawn intentionally because it is valid for bridge rectifier as well as center tap configuration. So here if we see that input voltage after rectification we are getting in the one direction. So all these half cycles are converted in the one direction. So if we consider this in terms of theta, then theta to pi, pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi, and so on, it will go on. And same thing we will observe in case of current also. So how do we find it? These are the steps, basically 3 steps we will be following. So first we need to find the average or DC output current, then we have to find the RMS current, and now we will substitute the values of the DC output current and RMS current in equation 1, that is this equation. In this equation this IDC and IRMS, these two values will be substituting. So to find the output DC current, we know that first we are starting with the voltage. We can start with current also. So here VDC is equal to area under the curve divided by base. Now if we have a look here, so area under the curve, that means here if we find the entire area under this particular half cycle, that will be sufficient because this is symmetric, or we can do it in this way, 0 to pi and pi to 2 pi divided by 2 pi, or we can integrate only 0 to pi and divide by pi. So both approach you can take, will get the same result. So here I have taken 0 to pi, integration 0 to pi V naught, and integrating it with respect to theta. So here we are substituting the value of V naught. So V naught is nothing but Vm sin theta, that is it is following the input voltage whenever it is just V naught is following the input, and input is also given as Vm sin theta. So 0 to pi and 1 by pi, we are dividing the entire thing, divided by base, you see here. So pi is our base here, so 1 by pi we are putting. So sin theta integration is minus cos theta, and Vm is constant part, we are taking it out, and solving this what we are getting, the DC output voltage expression is twice Vm by pi. Now similarly we can find the IDC. So IDC is what? VDC divided by all the resistors in the circuit. So that is twice of VDC we have found as twice of Vm by pi. So this value we are substituting here, twice of Vm by pi. But we know this value, this particular value, Vm divided by RL plus RF plus RS. So this value is nothing but Im. So substituting this value with Im in this equation, we can get it as IDC is equal to twice of Im by pi. So let us call it equation number 2. Next we will be finding the RMS current. So RMS current, for that once again we will be starting with this Vrms. We are finding first Vrms, then we will extend that to find the current. So Vrms, that is 1 by pi, that is base part, integrating it 0 to pi. Now V0 square. So this is giving us the mean, this is giving us the square, and whole thing should be under root. So half we are taking. Now if we are solving this, only one important thing, you have to convert this sine square theta in this form, 1 by 2, 1 minus cos twice theta, and then you solve this integration. So after solving this integration, what we obtain is Vrms equal to Vm by root 2, Vm by root 2. Now same concept, previous slide, whatever we have seen, that here IRMS we can find with the same relations, and finally we shall replace it with Im equal to Vm divided by RL plus RF plus RS. So extending that idea here, we can find IRMS as Im by root 2. So now we have the expression for IRMS and IDC in terms of Im. So now we shall substitute these values in equation 1. So if we substitute these values in equation 1, so we are getting this thing, and this Im get cancelled, and simplifying we obtain it as 8 by pi square, and 1 divided by 1 plus RF plus RS by RL. So is further converted into decimal. So 8 by pi square, that will get as 0.812. And now if this is the expression for the efficiency of a full wave rectifier, both bridge rectifier as well as center tap transformer based rectifier, full wave rectifier. Now if RL is much greater than RF plus RS, so in this expression this will tend towards 0, and we can ignore this particular equation. So we obtain that maximum efficiency of a full wave rectifier is 0.812, that signifies 81.2%. So 81.2% is the maximum efficiency of a full wave rectifier. So that is the end of this discussion, and join me in next lecture where we will find the ripple factor. Thank you.